Hello, this video begins a series on growth models. So let me give you an overview of what we're getting into so you can see what's coming up and how it's connected. All right, so we're starting with different kinds of growth models. Linear, exponential, and logistic are three very common growth models studied in biology. They're used in chemistry and especially finance, especially these two. So we're going to look at some in the next week, in the next unit. Well, it's still the same unit, but next week, some pretty involved applications of these models in finance. All right. So I'm going to start sharing my screen so I can draw a little better. And let's talk about growth models. The most basic growth model is the linear growth model. And it occurs when numbers are added or subtracted each time period. So here's a simple example. You got $20 in your bank, you add $5 each week. How much money are you gonna have in 4 weeks? So to model this, you might be able to answer this straight up, but I'm gonna go through some thought processes that will help us to abstract and generate some deeper models that we'll use. Okay, this is a useful process in mathematics. So our thought process is when n is 0, that's now. We got $20 in the bank. So when n is 1, we're going to add $5 to give us 25. Okay, that's simple. That's 1 week. When n is 2, that's going to be 2 weeks. I'm going to add $5 more, so 30, and so on. Oops, excuse me. I don't know what just happened. Here we go. So adding $5 each time period shows us something that we're going to call the common difference. I'm going to call that D is $5. And one way we can model this is by taking the current time and making that from the previous time, actually the amount of the previous time. And then adding that common difference. So if Pn is the current time, well, the previous time would be Pn minus 1. I'll show you what this looks like in an example. So if time is P4, we want to find the amount at 4 weeks. Well, we would take P4 minus 1 and add our common difference. I'll write it like D, which is 5. So we'll add $5. Okay, what's P3? Oh my goodness, why is it doing that? P3, how do we find P3? Oh, P3 is Pn minus 1. So if we subtract 1, that's 2 plus 5. What's P2? Well, that was P1 plus 5. What was P1? P1 was P0 plus 5. And P0 was 20. So we got 25. Put in the 25 here, that's 30. Put in the 30 here, that's 35. Put in the 30 here, that's 40. So this whole process is called recursion. You might be like, why do we do this? This looks kind of cumbersome. And yes, it is. Although it's kind of used in programming quite a bit. So this process, this recursive formula, the nice thing about this formula is it's super easy to set up. Okay, you just take the previous amount, add D to it. Okay, but there is another way we can think about this problem. If we don't want to use recursion, especially for the case of maybe I want to find the amount after a year. That's 52 weeks from now. So P52, I don't want to do this 52 times. Okay, there is a better way. Here's the logic. We could say, hey, I put in $5 each week for 52 weeks. That's 5 times 52, 260. So that logic is what we will use to create what's called the explicit formula. So the explicit formula here is modeled like this. Pn is the amount now, or n weeks from now, I guess you would call it. So Pn is the amount you want, I'll say. Now in n weeks, it's just the initial amount plus the difference times the number of weeks. So the initial amount is P0, the difference is D, and the number of weeks is N. We got our formula Pn equals P0 plus Dn. Okay, so let's use it for this example. The initial amount was $20. The difference was $5 a week, and we're looking at the difference after 52 weeks. So you get 20 plus 260 is 280. Okay. So what gives? That was a lot of work for what's probably some of you could have done in your head. Well, this thinking, these formulas, which I elaborated, here is the explicit formula. That's kind of small to read. The recursive is here that we already talked about. These formulas are useful in a wide variety of problems, ones by which you sometimes cannot think about them all in one step. So here's an example. I got elk that's being modeled, elk population. We know in 2003, the population is 1,200. It's 12,000 in 2007. It's 15,000. So there's two questions. How much is it changing each year? And then we also want to know, how can we project that change into the future to find out what the population is in, say, 2014? Okay, so that's what we want to use our growth models for. So let's first find out how much it's changing each year. So the change, constant rate of change, this is D, is the change over the number of years it's changed in. So how much did it change between these two time periods? You can see the change was 3,000, and the number of years here was 4 years. Okay. This rate of change, you also might remember from the equation that looks like this: y2 minus y1 over x2 minus x1. This is the change of some output value over the change of some kind of input values, is how we think of it in algebra. So think about it this way: y2 is the second time, or the second population, y1 is the first. And x2 usually refers to time. So this is x second time and the first time. So 2007 minus 2003, you see is the same calculation as before. So slope is rate of change. All right. So we found the rate of change. It's changing 750 elk per year, if you want to label for it. That's what we just found. That's the first step. Once we find that value for the rate of change, now we can set up our formulas. So let's do the recursive formula first, just for practice. Pn is going to be Pn minus 1 plus the common difference. And with the recursive formula, we do need to know what the initial value is. Otherwise, we get to 0 and we're kind of like stumped. So we're going to call 2003 n equals 0. That'll be the initial value, 2003. This corresponds to 2003. Excuse me, I got some allergies. And so all we got to know is what is this common difference? 750. So what this plugs in as looks like that formula there, if you plug it all in right. All right, so now let's look at the explicit formula. See if you can figure it out on your own. Explicit formula. We got all the same information here. We got D, we got P naught. And the only thing that's different about the explicit is it's P0 plus D times N. So Pn is what we want to find. P naught, 12,000. D is 750. So that'll be our explicit formula. And this is the one we'll most likely use. This shows us kind of a understanding of what's going on, the recursive. Explicit is the one we can use more easily to project into the future. So what's happening in 2014? 2014, we just have to figure out what that is in terms of N. So remember, N is years after 2003 is what we said. So if 2003 is N equals 0, 2004 is N equals 1, and so on, what is 2014? Okay, once you see that set up, we should see that N is 11 years after 2003. So we put in 11 here, P11, the population at 11 years. And solve that. Do I see my work? I don't have my work. I'll let you find that for the quiz. All right, so here's another quiz question I'll give you, and the rest of this we'll do in class. So that is all for this video. I will see you in the next one.